So the next question, stators in a gas turbine are designed to increase the kinetic energy of the gas passing through them adiabatically. Air flows steadily into a set of these nozzles at 2 megapascals at 371 degrees Celsius with a velocity of 24.4 meters per second and leaves these nozzles at 1.724 megapascals at 341 degrees Celsius. The question is, what is the velocity at the exit of these nozzles? So immediately from looking at this question, we can see that we're going to have a bit of a hard time using the simply m dot equals rho AV. And that's because we don't know anything about the area. We're never told the inlet, the exit area. So what's our other option? Well, we can consult the first law of thermodynamics. Now, again, these are sort of considered as nozzles. You have Q dot, like last time, equals 0, W dot equals 0. So we're going to end up with a very similar, well, actually the same formulation of the first law as we had before. And what will that look like? Well, since Q dot and W dot are 0, the left-hand side is 0. We're going to do it on a per unit mass basis. We're dividing through by m dot, and we're left just with H2 minus H1 plus 1 over 2,000 V2 squared minus V1 squared. Now, if we manipulate this a little bit, and we isolate for V2, what would that look like? Well, what we can do is this. We can say H1 plus V1 squared over 2,000. And remember, we're looking for V2 here. Equals H2 plus V2 squared over 2,000, which we can manipulate a little bit more. H1 minus H2 plus V1 squared over 2,000 equals V2 squared over 2,000. And then if we multiply by 2,000, we get 2,000 times H1 minus H2 plus V1 squared equals V2 squared. And if we take the square root of that entire expression, we should end up with something that will let us solve explicitly for V2. Now, one thing to note, yes, we know the inlet velocity. We do not, however, know explicitly the change in enthalpy. But what do we know? We know that for an ideal gas, which we will approximate this as, the change in enthalpy is Cp delta T. And do we know the change in temperature? Yes, because we're told the temperature at the beginning and at the end. Okay, so now what we have to do is just plug in. Again, whenever we're talking about temperature and ideal gas law, we want to generally use Kelvin. Here it's a change in temperature, so it doesn't really matter because Celsius and Kelvin increment the same way. But just it's a good habit to use Kelvin anyway, just because you can never really go wrong. So V2 equals the square root of 2,000 times Cp, which is 1.008, which is, this is for what we're using. The Cp is 1.008 kilojoules per kilogram Kelvin. Times the change in temperature, and notice it's 1 minus 2, not 2 minus 1. Temperature 1, again, by incrementing it to 273 extra to get in Kelvin, we're going 644 minus 614. And then, of course, we're adding plus V1 squared. And we're told that V1 is 24.4 meters per second. And taking the square root of all that, we'll get a velocity at the end of 247 meters per second.